Good day, dear colleagues. Today, we are going to present our project about anomaly detection using self-supervised point clouds. Here is a brief outline for today's talk. First of all, what is anomaly? Generally speaking, anomaly is just a sample which belongs to the distribution which is different from the class which we suppose as a normal. For instance, in case of image recognition, if you have images of people, for instance, celebrities, and one of the image which we have in our data set is dog or cat, just another animal, we suppose this is an outlier and we need to detect it. Why it is important to use self-supervised learning in outlier detection? First of all, label data is rather expensive. Exist different platforms when businesses or scientists need to pay money for label their data. But self-supervised learning allows to use unlabeled data and produce embeddings, reasonable embeddings, which then might be passed into the detector in order to understand which class is negative and which class is positive, or in other words, which object is outlier and which object is normal objects. The question here is what we need to pass to our detector in order to produce a reasonable representation of initial data. For these purposes, we use the following concept, which called point clouds. Point clouds in general words is just a set of embeddings which produced from the linear layer of self-supervised model. Here you can see a toy example how it can look like, and the most important point here is that this representation should be invariant to the augmentation which we apply to our data.
Based on a literature review, we found a number of state-of-the-art architectures, which principal schemes you can see on the slide. For all of these models, the common goal of mentioned contrastive learning methods is to minimize the difference of obtaining two random augmentations from a preselected set of transformations in order to obtain embedding space projections which are able to distinguish between different classes of initial data sets. Some of realizations based on these architectures may be very time consuming, and the most simple realizations that we can highlight is SimCLR and BarlowTwins. This slide represents a comparison of performance for different models using the linear evaluation on ImageNet, and the both mentioned models demonstrates decent performance with reasonable number of parameters. In this work, our goal is to construct a pipeline for a self-supervised point cloud similarity evaluation, and we take the existing architectures and train it on a single dataset class. The next step is to extract embeddings for all the classes and to apply some metrics and extract similarities. Among the various architectures, we have considered SimCLR as one of the best implementations, as well as the BarlowTwins. We consider it as one of the newest compared to all the others. In addition, these models are interesting, related to the low complexity, and both models is easy to implement. Finally, consider it as a new method. The BarlowTwins demonstrates performance, which can be compared with most modern and popular methods as PIOL and also SimCLR. Since it is the newest among the presented methods, it also of interest for testing in various conditions, and compare these models with the closest to it, SimCLR. We use both models with the same sets of the augmentation that you can see on this slide.
To check our hypothesis, we constructed a pipeline using two models with similar optimizer and parameters. For both models, we used the same backbone, which is suitable for self-supervised dataset, and we have two learning curves up to 100 and 140 epochs. We used in our experimental set, we used Tesla V100 GPUs on Colab notebook.
When the model is trained, we are ready to construct the point clouds and then score the similarity between them using the following scoring procedure. First of all, we need 3 data sets. 2 of them are the normal, test and train, and the third is anomaly objects. Then we construct using our neural networks the point clouds out of the embeddings of these data sets. And then using the bootstrap procedure, we construct a lot of randomly sampled subsets out of point clouds for each data set. Then we use some metrics and construct the distribution of similarity scoring for normal test and normal train data set, and do the same for anomaly object and normal object from the train data set. And in ideal case, we should observe 2 absolutely different distributions, and we can construct the threshold for separating normal and abnormal objects. However, it should be in ideal life, but we are in the real world. And in our case, we obtain the following results. First of all, we use 3 different metrics. These are Euclidean distance, manifold topology divergence, and Hausdorff distance. And we applied these metrics to our neural networks. And as you could see, for example, for Euclidean distance, we cannot distinguish cats and dogs. However, cats and airplanes can be separated fully. And when we used Hausdorff and MTopDiv scoring metrics, we obtained almost the same results. We could see that scores for cats and for dogs are similar, while for the other classes from the data sets, the scores are higher. It means that our neural networks can distinguish animals cannot distinguish animals, while the animals can be separated from the mechanical objects. In the conclusion, well, you could see here the example of the distributions for the BarlowTwins constructed embeddings using Hausdorff distance for each class from the data set. And as you could see here, it's really difficult to construct the threshold for the distributions for normal and abnormal objects. And to improve the accuracy and the precision and performance of our networks, we suggest the following steps. And these are the training on the multi-class instead of one class. Also, we can extend the data sets to, for example, larger images. And also, we should use different augmentations and perform the search on how the augmentations affects the separation threshold of the data set from normal and abnormal objects. So that's it. Thank you for your attention.